Hi everyone, this is week 13. We will cover integration techniques today, okay? So after today, we will be done with the integration techniques and the only remaining topic will be improper integrals, which is the topic of next week. So let's start with the first example. Here, we will study how to integrate products of sines and cosine with some big powers. So for this part, I want to show you some diagram that I drew you in the lecture template while recording the lecture videos. So the topic today is trigonometric integrals. So we can divide this part into two groups like that. The first group is products of powers of sines and cosine. Second group, products of powers of tangent and secant, okay? We divide into two groups like that. And then now I will be solving some questions from the first group. So let me summarize this diagram. You will look at the powers of sine and cosine. And if at least one of the powers is odd, as it is emphasized here, there are some certain substitutions to use. If the power of sine is odd, you will choose your substitution as the other one, cosine. If the power of cosine is odd, then you will choose the other function as your substitution. These substitutions are fixed depending on the power and they work for sure. And the last case is if both powers are odd, then either substitution will work, either cosine x or sine x. Both substitution will work. And then what happens if both of the powers are even? So this is the only remaining case after covering the case when at least one of the powers is odd. You do this kind of substitutions. And the remaining case, if both powers are even, you will be using these half angle formulas, okay? So this is the first group and this is the summarizing diagram. So let me apply this part on the questions. Okay, look at the first example. Here, look at the power, please, first. We have just sine. You can think of like there is also cosine here with the power 0. So one of the powers is odd. The power of the sine function is odd. So you will choose the non-odd powered one as your substitution, okay, as described in the diagram that I showed you. So you will choose the other function as your substitution, cosine x, and let's try to transform our integral according to this substitution. If u is cosine x, what is du? It is minus sine x dx. Then you can rewrite the integral x. You see, we have sine x dx inside du, so I will separate one of the sine function to serve as du, like that, okay? So this part now is what? It is minus du, right? And this part, now I need to rewrite this part in terms of cosine. Is there a way to transform sine to the power 4x to some expression including just cosine? Yeah, that's possible. How can you do that is the following. So you can write it like that, and sine square here can be written in terms of 1 minus cosine square like that. So we did that. We transformed sine to the power 4x function to cosine function like that. So it is, in fact, u is cosine x, so 1 minus u squared squared. So what do we have as the integral then? Minus goes out. Here we have 1 minus u squared squared du. You see, it is that simple now. You will just compute this square here, 1 minus 2 u squared plus u to the power 4 du, and then you evaluate. Integral of 1 in terms of u is just u. Integral of u squared, add 1 to the power, divide by the same power. Add 1 to the power, divide by it. And then what happens? Since this is an indefinite integral, you will add this arbitrary constant c at the end. So finally, you can do back substitution to turn back to your original variable x. What is u? U is cosine x, right? So in terms of u, I will be putting cosine x everywhere. Cosine x, then minus 2 over 3 u cube, and then u to the power 5 over 5 plus c, where u is cosine x. Okay, so this is your final result for the first integral. Any questions? Okay, then if no questions, I will continue with the next example. Again, look at powers. Both powers are odd, meaning that no matter which substitution you choose, it will work. And I think I will prefer to use this substitution only just for not having minus sign in the derivative. I prefer this one. So the derivative of sine 2x is cosine 2x times 2 dx. Okay, let's try to rearrange the terms here so that I can use these two. One of the cosine should be separated to serve as du, right? So that's why I will separate one of the cosines like that. Cosine 2x dx. Okay, what is cosine 2x dx in terms of du? There is this extra coefficient 2. Be careful. So this part is du over 2. This is u to the power 5. And now I need to express cosine square 2x in terms of sine square. And we can do it like that, sine square 2x. Then this can be written in terms of u like that, right? Okay, what we have is the following. So we have 1 minus u squared, u to the power 5 du over 2. This is what we have. And this is something easy to integrate after you do this multiplication. Just multiply. We have u to the power 5, u to the power 7 du, right? So 1 over 2. Integrate u to the power 6 over 6. I add 1 to the power, divide by the same power. And then finally, you can do back substitution. You should turn back the original variable x. Back substitution is like that. Something to the power 6 divided by 6. 8 divided by 8 plus this arbitrary constant c, where u is this one, sine 2x. Okay, this is your final answer for this question. Okay, any questions? If not, we can move to the next example. Look at the powers again, 4 and 1. So we have an even power and an odd power here. So how do we choose our substitution? If at least one of the powers is odd, you choose the non-odd powered one, even power, as your substitution, like that. Then du is cosine x, sorry, it is 2x, not x, but 2x times 2 dx. This question is very similar to the previous one. So this part is, in fact, du over 2, and this part is u to the power 4. du over 2. So it is very simple. Something to the power 5 divided by 5, and we have this 1 over 2 there, where u is sine 2x. And you need to add this arbitrary constant c at the end, okay? If you choose the correct substitution, everything becomes very clear in a second. If no questions, let's move on to the next example. So here we have even power. There is no odd power around. Both of the powers are even. You can assume that there is this sine to the power 0 2 pi x here, even power with an even power 0. So, but if we have both powers are odd, you need, let me put a recall here. You need to put half-angle formulas. So cosine square x is 1 plus cosine 2x over 2. There is a very similar formula for sine square x. Almost the same with this plus minus difference here. So let's apply this half-angle formula for our integration. You can rewrite this as cosine square 2 pi x dx, but the power is 4 here, so I need to square it again like that. So For this part, I will use this half angle formula. Be careful. You are doubling the angle here. If it is x on the left, it is 2x on the right. So you will multiply the angle by 2. So I will write here cosine, double this angle please, 4 pi x over 2. And you see there is another square there. Okay. So let me emphasize the angle is doubled here. Then what we have? Then let's compute the square. Okay, compute the square, please. 1 square of 1, 2 times cosine 4 pi x plus cosine square 4 pi x divided by square of 2, which is 4. And I will write this over 4 part to here, okay? Then what we have? Then we have to start integrating. Integral of 1 with respect to x is 1. X, right? Integral of 1 is x plus 2 times integral of this part. You should be careful about this constant. So it is sine 4 pi x divided by that constant. You already know this rule, how to integrate such trigonometric cosine kx or sine kx is integrated like this, plus integration of this part cosine square 4 pi x, right? Okay, for the integral of it, we will be using this half angle formula again. Okay, so this is what? We will double this angle again. So it goes like, use this formula, 1 plus cosine double this angle 8 pi x over 2. So you can integrate it now. By the way, I need to put the x here. Don't forget to put the x's. Okay, what we have here is 2 times x plus 2 times sine 4 pi x over 4 pi plus 1 over 2 goes out. And then this 2, maybe I should also change the color. 1 over 2, integral of 1 with respect to x is x plus integration of this. Okay, where we doubled the angle. So integration of cosine 8 pi x is sine 8 pi x divided by 8 pi. So that's it. And since this is an indefinite integral without any boundaries, you need to add this arbitrary constant c at the end. Okay? Any question? If not, I want to move on. So no questions. Okay, now we will be dealing some other type. I mean, this is a bit different than the previous questions, but still related to half angle formulas. Let me rewrite it again. I think we will be using sine square x here. So sine square x is 1 minus cosine 2x over 2. Can you compare these two expressions, please? They are almost the same, except this angle, right? So when you have x here, you have 2x here. And I want to rewrite this part again in terms of sine square. So it is sine square. If you have x here, you need to have some half angle on the left side, right? So what should I write here? X over 2, right? So this is half angle. That's why we call it half angle formula. X over 2x. So it's like that. And what we have from 0 to 2 pi inside the square root, we have x squared x over 2 dx. Okay, let's eliminate square root over this square. You know, you should always use absolute value function if you are evaluating something like this. This is always with absolute sign. That's why I will write here absolute signs of sine x over 2 function like this. Okay. If you want to evaluate the integral here, you need to evaluate the absolute sign first. And for that, you need to understand the value of this function, whether it is positive or negative. So look at the boundaries for x. X depends on, differs between 0 and 2 pi. Let's write this down. X is between 0 and 2 pi. X is from this interval. Then, what about x over 2? You can divide both sides with 2. So 0 and pi. So you have this angle here, x over 2, and this angle, whatever it is, depends on, it differs between 0 and pi. And if your angle is between 0 and pi, what about the sine values of it? So we can draw our unit circle here and try to understand what is this, what are the values of sine function over here from 0 to pi. So over here, sine is always positive. Over also here in the second quadrant, sine function always gets positive values, right? That's why you can evaluate this absolute sine without doing anything. From 0 to 2 pi, absolute sine of sine theta is, again, sine x over 2, because sine takes the values always positive if your angle is between 0 to pi, like that. So it is just sine x over 2 dx, okay? Is this part understood? So we look at the unit circle to understand the values of this function, and we see that it is always positive. If the angle is between 0 to pi, sine function always gets positive values. That's why I just removed the absolute sign without doing anything. And then the rest is just computation. The integration of sine is cosine, and then you also need to divide by that coefficient here. And then you need to insert these upper lower bounds for your x. So the result is 2 times, by the way, this is minus cosine. So the result is minus 2 times cosine of insert 2 pi over 2 minus, I just removed this minus 2 coefficient out. So this is minus cosine 0 over 2. But this is cosine pi is minus 1. Cosine 0 is 1. So the result is, I guess, 4, right? So that's how you evaluate square roots, by transforming the inner function to a perfect square, okay? After writing this expression as a perfect square, you can only then you can eliminate square root by using the absolute sign, and then you need to be careful about the sign of the function inside the absolute value, and then you can, after getting rid of the absolute value, you can integrate. Any questions? Okay, then let's do this similar question. 1 over sine squared theta can be written as cosine squared theta directly. So this integral is in fact square root of cosine squared t dt. And then we are ready now to evaluate the square root with this square. That's why, okay, so that's why I put absolute value sign here, okay? And then look at the unit circle to understand the signs of the function cosine over this interval. So these are the boundaries for t. So t is between 0 and pi. So from here to here, your t changes. Look at the, try to understand the values of cosine function. So from here to here, cosine takes positive values because of the x components are positive. And from here to here, cosine takes negative values because in the second quadrant, x components are negative. What does this mean? Then how can I evaluate absolute sign? That means that, over this interval, on some part of it, cosine t is positive, on some part of it, cosine t is negative. That's why I will divide the interval into 2 parts like that. Cosine t dt, and then I will continue from pi over 2 again to pi, cosine t dt. Okay. Over this interval, cosine t is positive. Over this interval from pi over 2 to pi, cosine t is negative. And this gives us the clue about how to take the absolute sign value. So since it is positive, I directly remove the absolute sign. Since this is negative, I will put an extra minus sign in front of it while evaluating the absolute sign, like that. And then the next line will be evaluating the integrals. Integral of cosine t is sine t from 0 to pi over 2, minus, again, integrals are the same, pi over 2 to pi. So this is a definite integral, so evaluate at the upper lower bounds. Now, sine pi over 2 minus sine 0 minus sine pi minus sine pi over 2. Okay, sine pi over 2 is 1, this is 0, this is 0, this is 1. So the result is minus minus is a plus, so it is 2, right? Okay, that's how you should treat such type of integrals, including square roots, and where you can rewrite the inner function as a perfect square. Okay. If no questions about this solution, I want to move on with the next example. Okay, then let's move on. Now it is time to cover the second column in that diagram, products of secants and tangents with some high powers. About this part, let me tell you something. If you look at your lecture notes, let me show it. If you look at lecture notes, you will see that I didn't put any sub cases, which explains you if this happens, use this substitution. I didn't put any substitutions here because there are much more sub cases here than we have in the first column. So it is a bit complicated, too many cases, saying that this happens and use this substitution. Instead, I don't want to confuse your mind with writing lots of sub-cases here. Instead, all I can tell you that you will try to use one of the substitutions, secant x or tangent x, which makes sense because these are the only type of functions here. One of them will definitely work, and you will see it by trial and error, but on the way, you will also be using these two trigonometric identities, okay? Secant square theta x is tangent square x plus 1, or this is the same line. You can write it in this form. Tangent square x is secant square x minus 1. So instead of having lots of such cases here, please keep this in mind. Either u equals secant x or u equals tangent x substitution will work, and you will, on the way, you will be using this trigonometric identity. And here are some particular cases where we have really less power, like n should be 2, m should be 0. Integral of secant square x dx is a rule because derivative of tangent x is secant square x, right? And this is also a rule. Secant times tangent you may have. So tell me a function whose derivative is secant times tangent. Of course, it is secant x. And this is also a rule that I covered in the previous weeks. Integral of secant x is given by this rule. Let me put here some rules. You should know them as rules from now on. And you may also have tangent x dx, and I will explain it in my example. Okay, so that's a quick recall for us. And let me try this example now. Okay, we will be using secant square x, secant square x. There is a trigonometric identity for that, depending on tangent square like that. So to be able to use it, you should decrease this power. You should separate some powers. This will always be your strategy while handling the integrals of products of tangents and secants like that. Okay, now we can start using some substitution. You will get used to it after a few examples. If you call tangent x as your u, you will have the derivative like that. So I understand that this seems like the correct substitution because then this part is u square and this is exactly what the u is. And This also can be transformed into tangent like that, right? This is secant square x is already given as tangent square x plus 1, and this is now written in terms of u like that. See? Very quickly, we transform the integral into u's and du's like that. It is u square plus 1 times u square and du. Then all you need to do is to do this multiplication. Let's do this product. It is u to the power 4 times u square du, and then you add 1 to the power, divide by the same power. It is an indefinite integral, and the final line should be back substitution, u cubed over 3 plus an arbitrary constant c. U was tangent x, remember, so you need to turn back to your original variable x by applying back substitution like this, okay? So let me show you more examples of this kind and you will get used to that. If you have secant to the power 4 theta d theta, first thing that you can do, there is only one thing that you can do here, separating secant squares like that. There is nothing to do. Only the first step is so obvious, and inserting this for one of the secant squares, okay? So let's insert tangent square theta plus 1 for this one. And then what you will do, you will multiply this with this thing. Okay, let me write this down. We write tangent square theta plus 1 there, and then we have this theta. Okay, so do this multiplication, please, like that. And what we have tangent square theta, secant square theta, d theta plus, I am writing the second integral separately like this. Okay, and look at here now. The substitution is kind of obvious again, as we did in the previous example. If you choose tangent theta as your substitution, if this is u square, then this is exactly du. Can you understand that no matter how high power you have, as for the tangent function, as long as you have secant square theta d theta near it, this serves as du, and this is u to the power 100. I mean, this always works. As long as you have secant square theta d theta near the tangent function, the power doesn't matter. This substitution is always working. Okay, this is u square du. Then what we have, let's start integrating. U square du is integrated as u to the power 3 over 3, right? And then this second integral we have. Tell me a function whose derivative is secant square. This is a rule, okay? This is not solving another example. You should learn this as a rule. Tell me a function whose derivative is secant square. There is such a function, and it is tangent function, of course. So this is u square du is integrated as u cubed over 3. So where u is tangent theta. So this is your result then, with this arbitrary constant c, because it is an indefinite integral. Be careful. Is that okay? Can I move to the next example now? I guess no questions, right? So let's try the next one. Okay, we are always applying the same strategy. You should always separate some square from the given function, okay? Always separate square part from that. Why we are doing that? Because only then you can use the trigonometric identity. Let me write this down again here. I'm sorry. Okay. Secant square x is tangent x square plus 1. Like this. And you can rewrite this equality in this form. So tangent square x is secant square x minus 1. So I am inserting it here. Tangent square x is secant square x minus 1. Then do this multiplication. What we have? Tangent cube times secant square x. And this is a nice thing. Remember what I did tell you in the previous example. As long as you have secant square x dx near tangent, the power doesn't matter. It is handled by naming tangent as your u. We also have this multiplication, tangent cube x times minus 1. So second part looks like that. Okay, for this part, if you choose u equals tangent x, it is handled. So this is u cubed, this is du. For this one, you will do the same, okay? So you will separate, it is kind of the very same example with the power 3 instead of 5. So you will do the same strategy. You will tangent write it like that, okay? And then for tangent square, you will write secant square x minus 1, just like we did before, and then you will do this multiplication. Then what you have. Okay, let me write this down. What do we have here? Tangent cube u, sorry, u cube du. It is u to the power 4. You know, this integral is u to the power 4 over 4. That's why I can write it like to the power 4 over 4, where u is tangent x. Minus, now I am here, what do I have there? Do this multiplication. It is secant square x times tangent x. It's x times secant square x dx minus tangent times 1. Tangent x dx, okay? Like this. I just did this multiplication and separate the integral into two parts. And similarly again, if this is u, this is du. So you know how to integrate it. Let me write from the beginning on. Tangent x to the power 4 divided by 4 minus, this is u squared over 2, where u is again tangent x minus, what about the integral of tangent x? So you know tangent x is sine x over cosine x dx. You need to use a very quick substitution again. If you choose cosine x as your u, sine x dx is minus u. So this integral is minus du over u. So you integrate it. How to integrate du over u? Tell me a function whose derivative is 1 over u. So it is a ln function, right? So minus will be a plus. Ln absolute sine of u, where u is, this time u is cosine x. Okay? And then you also need to add this arbitrary constant c at the end because it's an indefinite integral. Okay, this is your final line, giving you the result. So can I move on? Any questions? I think since this is very similar to what we did above, I will leave this one as an exercise for you. You should try it by yourself. You know, getting used to how to solve integral question, it can be done. I mean, you shouldn't read the question. You should get your hands dirty to get used to integrating such functions. So this is the solution of the previous example. You should solve this by yourself. Take your pens, pencils, and write the solution on your own. Okay, let me move on if no questions. Is it okay? I think I will stop here before I move to the next group. But the second part is a bit longer. Maybe we should start giving a recall, then we can take the break. Okay, let me give you a very quick recall about the second part. Now we are covering a new integration technique, which is called trigonometric substitutions, and it goes like that. When do you apply trigonometric substitutions? Inside your integral, if you have this structure or a square minus x square structure, or x square minus a square. There are certain substitutions for all these three types. If this is the case, you will use this trigonometric substitution. Trigonometric substitutions are fixed like that. If this is the case, you will use a times sine theta, and if this is the case, it is a times secant theta. Okay, so these are fixed for all these types of integrals. What do I mean by that? For example, look at your first question. At the denominator, there is a structure, there is a square root function fitting to this one, right? Let me show you how it fits. So we have 1 plus 3x squared square root. It is exactly of this form, a square. Instead of x, you have 3x, doesn't matter, right? So this fits to this structure. That's why I will use 3x. What is a here? 1 corresponds to a square, so 1 times tangent theta. This will be the correct trigonometric substitution that will solve this example. Okay, let's apply it. How to apply it? Of course, you will take the derivative of both sides. 3dx is, what is the derivative of tangent? It is secant square theta d theta. Then let's transform our integral, which is in terms of the variable x, to some new integral, which will depend on theta. Be careful, by using trigonometric substitution, you will move from x variable to the new variable theta. After applying the trigonometric substitution, your new variable will be not x anymore, it will be theta, okay? That's why we call them as trigonometric substitutions. So, rewriting the integral. Instead of 3dx, I will directly write secant square theta d theta. And for the denominator, what do I have? Instead of 3x, which is squared here, I will write tangent. So this is tangent square theta. Do you remember our trigonometric identity for that? It is secant square theta d secant square theta. So inside the square root, we have secant square theta. Normally, this is the correct way of evaluating the square root with the absolute value. But remember, in the lecture video, we put some restrictions on the theta. You can check these restrictions, upper lower bounds for theta. So with those restrictions that we fixed while applying trigonometric substitutions, by fixing those restrictions on the theta, you make sure that secant theta takes always positive values, okay? These are all explained in the lecture notes. So this makes sure, these restrictions make sure that secant theta takes always positive values. That's why, while applying trigonometric substitutions, you don't need to worry about absolute sign. It will always be evaluated as itself because the function will always be positive. We force the function to get positive values by putting those restrictions in your lecture notes. Okay, so from now on, I will always be evaluating square root and squares directly without putting absolute sign. But it is there, it is always positive. That's why I am directly removing it, okay? That's the explanation. So from now on, we don't need to worry about absolute sign. So what we have then, it is secant square theta d theta divided by, just eliminate secant theta, right? Then you can simplify these two. What we have inside the integral is just secant theta d theta. Remember, this is a rule for you now. This is a rule. Integral of secant theta is ln secant theta plus tangent theta, okay? Don't forget, you should know this by heart from now on, and you should take this as a rule. By the way, I solved this integral in a very detailed way in the lecture video. If you wonder why this integral appears to be like that, you can go and watch lecture videos, or you can look at the lecture notes. This sounds a bit strange, but it is like that. You can check the lecture notes for the solution of it. Okay, we evaluated the integral, but we cannot leave it like this because our original variable is x, not theta. We need to turn back to our original variable. So we need to apply back substitution, turn back to x. For the trigonometric substitution examples, you can turn back only by using this reference triangle. What do I mean by reference triangle? Reference triangle. You look at your first line of substitution, okay? What do you see here? 3x is tangent theta. This was our substitution. So by using this information, you will decorate your reference triangle. What does tangent theta mean? It means opposite side divided by adjacent side, right? So I need to decorate it like this to have tangent theta as 3x. And then once you put 3x and 1, you can directly compute the hypotenuse this side by applying Pythagorean identity, right? Okay, then turn back to here. You see some trigonometric functions. By looking at this reference triangle now, you can read any type of trigonometric function. So what is secant theta? Secant theta is 1 over cosine theta. Read cosine theta from your reference triangle. What is it? Adjacent side divided by hypotenuse, right? So it is 1 over, okay, let me write this down. So this is what? Then this is 1 over, read cosine theta, 1 over 1 plus 9x square root. You see, secant theta can be found like that by using your reference triangle. So it goes like ln. So 1 over, this thing is the reverse of it, of course. 1 plus 9x square root plus tangent theta, 3x over 1. So you see, we turn back to our original variable x. How did we do that? We cannot do that by drawing this reference triangle. You have to draw it. So back substitution is done by looking at this reference triangle, okay? But this is our first example on trigonometric substitution. You first look at the structure here, and you will recognize it as one of the structures in our list. Then the substitution is fixed. Use the given substitution. Then insert your substitution to your example. At the end, you will obtain the new integral depending on the new variable theta. Do the integration, and then the result of the integral should be rewritten in terms of x. So you need to do back substitution. How to do that? By drawing a reference triangle like that. This reference triangle gives you everything to read such trigonometric functions in terms of x. Okay? So any questions?